Welcome to this next lecture on fundamentals of acoustics. We have seen a number of sources now. For example, we have seen a pulsating sphere. We have seen a piston in a baffle. We have seen a spherical piston on a sphere. We have also seen a point source on a sphere, and of course scattering from a rigid sphere. Okay, and pulsating sphere, we have seen the physics in some detail. Piston in a baffle also we have seen some detail. Today we will look at this spherical cap on the sphere, rigid sphere. So what we have here is there is a rigid sphere, okay, and in symmetrically placed there is a cap or a piston that is oscillating back and forth, and this half angle is alpha. That half angle is alpha. Okay. Now before I begin, let me just tell you that pressure expression for a typical source will have the following features. J omega rho will be there if it is velocity driven, okay, velocity driven, okay, like the pulsating sphere, it is driven by a velocity on the surface, or even the piston in a baffle, it is driven by a velocity, an oscillating piston. So J omega rho will be there. Then there will be the source strength Q, okay. In the case of the piston in a baffle, it was the area times the normal velocity, this will be there, and there will be something of an R dependence, distant dependence, pi r, 2 pi r, 4 pi r, etc. Okay, there will be that dependence. Okay, also there will be a dependence on Helmholtz number Ka by 1 plus jKa, something of that nature. Okay, so all these are likely to be there. This is one term. Okay, so this is one term, this is another term, this is another term, and lastly there will be an angular dependence, okay, just as we had J1 Ka sin theta by Ka sin theta, an angular dependence. Okay, all these four entities will come in a product in some manner or the other. Okay, the form will change a little bit. Okay, so these four terms will be there when you describe pressure from a source. Okay, so now we are going to look at this case of a piston on a rigid sphere, for which we have derived all the expressions. Okay, so now what I am going to do is we are looking numerically computed cases. Okay, so first case, okay, is going to be at 300 hertz, okay, where the wavelength is about a third of a foot, okay, 12 inches by 3, 4 inches, about 4 inches is the wavelength, okay, and the K in air is 5.54, wave number is 5.54, okay, And what are we going to do? I have this radiating piston angle over this rigid sphere. Okay. So, starting with this half angle of pi by 32, I am going to increment it in 5 steps: pi by 16, pi by 18, pi by 4 and pi by 2. Okay. So, by the time the half angle is pi by 2, then I have covered half the rigid sphere. Okay. This much of the sphere is actually vibrating. Okay. So, I am increasing the angular extent of the radiator, angular extent of the piston. So, alpha first case is pi by 32 and it increases till pi by 2. Okay. So, this is pi by 32, this is pi by 16, pi by 8, pi by 4, pi by 2. Similarly on this side. Okay. Now, what is the difference between the two? On the left side, I am measuring at a radius of 0.1 meters, where the radius of the piston is 0.082. So, I am measuring just outside the radius. Okay. So, if this is my sphere, I am going to measure just outside. Okay. We will call it the near field. Call it the near field. So, this side will be the near field, whereas this side I am measuring at 1 meter. I am measuring at 1 meter. So, maybe it is in the far field. Okay. So, these are the pressure plots in dB, computed in dB, but I would not want you to focus on the numerical value of the dB. It is unimportant. Okay. So, what does the left side say? Here the extent of the radiator is small, here the extent of the radiator is becoming bigger. At pi by 2, this is the extent of the radiator. Okay. And measuring very close to the radiator, what we see is the pressure kind of follows very closely the nature of the radiator. Okay. The pressure is measured so much close to the surface that only the local region influences the pressure. There is not much influence from distant regions. Okay. So, now for pi by 2, you can see that this half angle is the radiator part. So, the pressure is pretty much constant there. Okay. And when you cross the half mark, the pressure follows the rigid surface and pressure drops off quite rapidly, because this part beyond pi by 2 it is not radiating, beyond pi by 2 it is not radiating. Okay. The measuring we are doing from theta equal to 0 to theta equal to pi. Okay. We are measuring all around. At a radius of 0.1, we are going to measure all around and come down 0 to pi. So, that is what this is 0 and it is pi. Okay. So, very close to the sphere. So, you can see that the pressure very closely follows the behavior of the surface, because it has to follow the boundary condition. Okay. Now, we go to the right side where we are measuring at r equal to 1, a little distance away from the surface, and again we are going all around. We are going from theta equal to 0 on top to theta equal to pi at the bottom, and this is spherically symmetric. So, the same thing will happen on the other side also. That is why we just have to plot 1. Okay. Now, here you can see that the variation is less. Variation from here to here is less. You can see the variation from here to here was quite a bit. Okay. Whereas from the left to the right, the variation is less. So we will call it smoothed out. Okay, the field gets smoothed out in the far field, the sound field gets smoothed out in the far field. Okay, the reason is that whereas when we are standing very close to the source, that region is dominantly influenced by the nearby surface. If I go far away, okay, this point is influenced by all the regions that are radiating, and so there is a smoothing effect that happens. Okay, and so there are not too many highs, there are not too many lows. Okay, it's almost a flat. Okay, the other reason for this being not so eventful, not having too many variations, is that the Ka is small, the Ka value is small. Okay, because the piston is a circular radiator, okay, as a spherical dimensions. So I have computed some typical dimension to represent the radiator and called that A or maybe A star, and multiplied with K to give me a Helmholtz number. That Helmholtz number goes from 0.08 at pi by 32 to 1.4 at pi by 2. Okay, so it's very close to 1, very close to 1, and therefore directivity is also much less. Okay, it's not very directive, it's close to a monopole, so it's almost radiating similarly in all directions. Okay, so that's the situation as 300 Hertz. Now if we move a little higher in frequency, if we move to a higher frequency, this is 1000 Hertz. The left side is R equal to 0.1 near field, and the right side is R equal to 1 far field as mentioned here, and the frequency has gone up. Okay, here the wavelength is about a foot. I should make a correction. Here the wavelength is, my mistake, is 3 feet about, not low frequency wavelength is long, is about 3 feet. Okay, you have a wavelength of 3 feet, almost a meter. Okay, and this radius of the piston, radius of the sphere is 0.082 meters. So you can see the wavelength is much larger than the radiator, and so the radiator has difficulty, so it behaves like a monopole. Okay, so now we go to the next situation here, which is 1000 Hertz. Okay, at 1000 Hertz the wavelength is about 1 foot. Okay, now distinct things to see is you are seeing variations, we are seeing variations in pressure from the front to the back. From the front to the back you are seeing variations. There is a dip happening here, there is a dip happening here. Okay, for the same reason there is more variation on the left side, because you are close to the surface. The surface pressure follows the boundary condition, and therefore you see variation. Okay, whereas on the right hand side it is more smoothed out as before, it's more smoothed out. Okay, and a dip is beginning to appear at some point. Okay, there is a dip that starts to appear. Okay, the reason for that dip I will let you know, but there is a change, there is an angular dependence now that is appearing in both left and right side, angular dependence. Okay, now let's go further down. This is 3000 hertz. Okay. So now more variations in pressure, more variations in pressure. Here the wavelength is a third of a foot, 1/3 of a foot. It's becoming smaller, perhaps coming closer and closer to the radius value. Okay. As a result of this, if just as it happened for the piston in a baffle, okay, different regions of the piston do send out their waves, okay, but because the wavelengths are now short, okay, they interfere with each other, and there will be regions of high and there will be regions of low due to interference. Okay, this interference is what is causing these oscillations, up and down behaviors, these up and down behaviors. Okay, again the lowest curve is for a short radiator, pi by 32 angle, the highest is pi by 2. Okay. Now because of the symmetry, this is symmetric, right, because of the symmetry, as the waves move backward this way and the waves move backward this way, they go through a decay because of distance, but at the end because of symmetry they are in phase, so they add, the waves add at theta equal to pi. Okay. So theta equal to 0 is at this end, theta equal to pi is at this end. Okay. So you can see at theta equal to pi there is an amplification. For all sizes of the radiators, suddenly there is a bump up. Okay. Another thing that you see is that this drop is more radical. This is at theta equal to 0. This is at theta equal to 0. Okay. As you move towards the back end, this drop is more radical, okay, more steep. That steepness is called the shadow effect. Shadow effect. Okay. For example, if there is a light source and there is some object over here, you will have maximum light coming in at the front. As you start moving around the object, the light level will start going down, and if there is a bigger object, light will go down even more. Okay. So this is the shadow effect due to the rigid sphere. So and so you get this drop. Okay. Now there is a dip that is happening. Okay. In the 1000 case the dip was a little more to the left. In the 3000 case the dip is moving towards the right. Okay. The dip is because now you have waves moving symmetrically on both sides. Okay. And so they come and they are in phase here because there is a point of symmetry. Okay. But now as this wave from this side moves over to the left, it is in phase here, but a little distance away it is out of phase here. So at some angle there is going to be a partial cancellation. Okay. Similarly on this side because of symmetry. So that is this cancellation. Okay. That means the waves coming from this side are interfering destructively with the waves that are coming from this side and meeting them here. Okay. And because this theta equal to pi is kind of a bright spot symmetry point where they add, as the wavelength goes down, that cancellation point will come closer and closer to the back end. Okay. So that's why at 1000 hertz, if you see, this dip was a little more to the left here, okay, whereas for 3000 hertz the dip has moved towards the right and it's sharper, okay. It's moved to the right because it has to be now closer to the bright spot, shorter wavelength, okay. From a peak a shorter wavelength away you will get a cancellation, that's why. Okay, and sharper also because the wavelengths are small, okay, small, okay, wavelength is small. Now another effect you will see is that whereas when the wavelength was big, lambda was big, okay, a meter and so forth, the whole radiator was looking like a small region, whereas when the wavelength has become small as the frequency has gone up, okay, as omega goes up, k goes up and lambda goes down, that's the way it happens, okay. So now the radiator is looking, okay, much bigger to the wavelength, okay. This radiator is now looking much bigger to the wavelength which is only this much, let us say, okay, and therefore there will be some cancellations on the surface of the radiator also. Whereas earlier the whole radiator was looking like a monopole, a short range radiator, a small size radiator. Now as the lambda has come down, okay, the A has started to look comparable or bigger than the lambda, okay, so that there will be local cancellations even on the radiator surface. As a result of that, okay, even so you will have this funny effects of where you could have a smaller radiators have high pressures, whereas a large radiator pi by 2 has some cancellation and it does not demonstrate the same level pressure, okay. It is all a game of interference and cancellations, okay, and it becomes more and more pronounced as you go higher in frequencies, okay. So let us see now. So there are some points I have made, they could be that could be a kind of a repetition. Small source has lower amplitude, that is for sure, okay. In all the cases this is the small source here, this is the largest source here, so the amplitude goes up, pressure amplitude goes up, okay, and the far field has a dip beyond 90 degrees. The sound field proceeds from both sides of the symmetric source, thus they must be in phase at 180 degrees, okay. Beyond there will be a location where they will be out of phase. This is best seen at high frequencies, where at the back side there is an amplification of zone and the two waves are in phase. However, just before and after they will be out of phase, and if the wavelength is small, then the dip will occur close to 180 degrees, okay. Then far field is smoothed out, that we have seen, because in the far field many parts of the radiator are reaching out to that point, so there is a smoothing effect, okay. And near field small source decays very quickly with angles, there is a shadow effect. The rigid sphere will reflect the sound field forward, and so as one moves around the sphere the field rapidly decreases. This is more pronounced if the rigid sphere radius itself is increased, we will see this case, okay. And at higher frequencies there will be more oscillations in the sound field, okay. Then as Ka goes up, there can be interference on the surface of the piston itself, so that the center of the piston can have a lower value, and thus many funny crossovers can be seen. And for the same angle of the source, as the rigid sphere radius is increased, the shadowing effect happens and more pronounced at higher frequency. This I will show, I said. Okay. Now the next case we are seeing is that we are going to increase the radiator size. Okay, the radiator angle we are going to increase in the same manner, pi by 32 to pi by 2, and we are going to look at the on axis pressure from the surface to a distance of 3 meters. Okay, from the surface of the radiator to 3 meters, we are going to plot the pressure at theta equal to 0. At theta equal to 0, R running from the surface A to 3 meters. Okay, and this plot is for 300 and 1000. Now if you recall what happened with a piston in a baffle, what you saw is that there are these interferences on the symmetric axis, and beyond you get a decay. Okay, this decay kind of happens in the far field. Okay, the far field is dependent on the frequency and the size of the radiator. Okay, at low frequencies for a small size, because the typical Ka is small now. Okay, typical Ka is small, we only have this 1 over R kind of decay that is happening. Okay, for each increment in the radiator size, the pressure goes up, fine, but from the surface of the radiator you see a 1 over R type decay. Okay, at theta equal to 0 for low frequencies. Okay, now if we move from 300 and 1000 to higher frequencies, the 3000 and 6000, let us say. Okay. So we have 3000 hertz on the left, 6000 hertz on the right. I am moving from A to 3 meters. Okay. And you will slowly see that it is behaving like the piston. So you're getting these interference patterns like the piston. Okay, why? Because the Ka effectively has gone up, either A has gone up or K has gone up, so that now at a certain point you have a path difference. You have a significant path difference that can account for a cancellation. Okay, and at 3000 and 6000 you can see it is just beginning to happen. It's just beginning to happen. Okay, if we go further at 12,000 and 18,000, you can see that it is again trying to repeat the piston in a baffle behavior. Piston in a baffle. Okay. Now these are some of the common points. Pressure is always maximum. I wouldn't say that. Largely. Okay. It all depends on Ka and how the waves line up to cancel. Okay, as frequency increases, oscillation increases. Okay, as frequency oscillation increases because of interference. Okay, unpredictable crossovers. Okay, there's an amplification point. Okay, the back end. Now for the shadowing effect. Okay, so here what I have done is that I have taken a constant angle pi by 8 for half angle. Okay, and what I have done is I have increased the radius of the sphere. I increase the radius of the sphere from the nominal value to 5 times, 5 times the value. Okay, that is what this says, A to 5 into 0.082. Okay. Now you can see that at the highest increment of the radius, how sharply the sound field drops. So we are measuring at 1 meter. Okay, so we are measuring 1 meter from the source and from 0 to pi, 0 to pi. So we are given theta equal to 0, theta equal to pi at a distance of 1 meter from the center. Okay. So now the angular extent is constant, but the radius of the sphere has been increased, the rigid sphere has been increased. Now you can see that at the highest increment of the radius, how sharply the sound field drops off. Okay. That means if you move from 0 to pi, you will start losing the sound level very rapidly. This is the shadowing effect. Okay. And of course, as usual, you have these interferences which are more and more, because lambda is getting reduced as omega is going up. Okay. And you have this amplification at the back end, that is due to symmetry. So these are some of the features, some of the most dominant features with respect to sound radiators. Okay. So all of these will in some effect, in some way or the other be present when you are looking at a radiator. There will be an angular dependence, there will be a radial dependence, there will be interferences, there will be this shadow effect. Okay. There will be the effect of the Helmholtz number. Okay. It will be efficient when Ka starts to become higher, it will be less efficient when Ka is much smaller than 1. Okay. So here the levels will be low, here the levels will be high, but here more interferences will come as Ka goes up, there will be more interference patterns. So these are very typical features of sound radiators. Okay. So I have just demonstrated that using the spherical cap on the rigid sphere or spherical piston on the rigid sphere. Okay. So with the pulsating sphere, with the piston in a baffle and a piston in a rigid sphere or a spherical cap on a rigid sphere, I hope you get enough of the physics of how sound radiators behave. Okay. In the next class we will proceed with that. I will close the exterior sound, I will close the topic of exterior sound, and then we will move to interior sound. Thank you.